In this lecture, we're going to do, you guessed it, another example of an ice table. But this time I'm going to make it a little bit more complicated. The past two examples we've seen had this really wonderful, perfect alignment of stars where we were able to take the square root of both sides of the equation and eliminate any x values that were had a power like an exponent component to it. And so that meant it was easy to algebraically solve the problem. Uh, Now, once we get into slightly more complicated chemical reactions that have a lot more actual particles involved in the overall reaction, we may run into more complicated solutions to solve for x. And so here's an example of one that's going to require the quadratic equation. Do you remember that? It's worth looking up again. The quadratic equation we're going to use for this chapter. I don't expect you to memorize it or have it memorized from when you learned it at first. I think when I saw this, it had been since like the fourth grade since I had used it. And I was like, oh man, now I got to do that again. Look it up, practice it, use it. And you can always double your check yourself with like quadratic calculators if you're feeling stressed. But you should practice using it because especially for chemistry exams like the ACS exam and things like that, they always make you actually calculate it out yourself. So with that introduction, let's walk through an example looking at acetic acid combining with ethanol to form ethyl acetate and water. And we have an equilibrium constant given to us that is 0.11 for concentrations. Now, this problem is giving us just concentrations right off the bat, which is kind of nice. So it's telling us we have an aqueous solution, so tons of water, of ethanol and acetic acid, and they each have, so they both have a concentration of 0.810 molarity. It's heated to 100 degrees Celsius. The important part is that temperature is going to be constant for the reaction. What are the concentrations of acetic acid, ethanol, and ethyl acetate at equilibrium? So that is what we're trying to figure out here. So we're going to use the same problem solving strategy we just saw. So let's go through those steps together. Step one, we write our equilibrium law. So we've got that right here. Something I'm going to point out about this one is that water is not included. It's not included because it is a pure liquid. It's the solvent to our reaction. We have so much of it around that it's not actually having an impact on where equilibrium lies. Also note that all of our coefficients here are 1. So we don't have any exponents to worry about in our equilibrium law. And you'll see this when we move on into acid-base chemistry next. We'll do a lot more ice tables. We're doing these the rest of the quarter. But they're all, for the most part, going to be 1-to-1-to-1 ratios. And so we're not actually going to have to manage the exponents when we're doing the final calculations of what x is. So we won't have to manage as many large exponents. That's a better way to say it. So we've got that. Let's build our ice table next. So I write out the chemical reaction right here. And I input the information that's been given to me. So that's my 0.81, 0.81 for my two reactants. I'm combining these together. So that means at that point in time, initially, I have 0 products around. So I have a concentration of 0. I'm now going to go through and add my change column. Because my coefficient is 1 for every single one of my reactants and products, I'm going to use a minus x and plus x. So that 1 coefficient is going to impact this. All right, and now I combine these together. I take my initial and my change, I add them up to get my equilibrium concentrations. So for both of my reactants, this is 0.810 minus x. And for my product, it's just x. Now I plug these back into my equilibrium expression. And so this is going to be x divided by 0.810 minus x. So remember, before we used the strategy of converting this or what is it? Simplifying this into 0.8010x squared. And when we had this was some sort of thing squared, we were able to take the square root of the whole thing. And we don't have that opportunity here, right? We can't take the square root, or we'd have a x to the exponent of 1/2 that we were solving for instead of x squared. So it doesn't really help us. So that means that we need to solve for x using the quadratic equation. So first we have to rearrange. So that's step one, rearrange. In doing that, I'm going to be able to first multiply out my two expressions that are in parentheses. And so this is coming, this is coming from that 0.810 minus x times 0.810 minus x. And remember from back in, algebra, we first multiply our firsts, and then our outer, then our inner, and then our last FOIL. And as we multiply those out, we're going to get this expression right here. And now we know that's going to be on the denominator of our equilibrium expression. So we multiply it on both sides. So this is times our k value right here. And that's equal to the x that was in our numerator from our expression. So we're going to simplify this more. We're going to set this up so it equals 0. So we have everything on one side. And so as we do that, we have finally the form for the quadratic equation, which is this right here, ax squared plus bx plus c equals 0. And now here's that moment you've all been waiting for when we bring in the quadratic and you're like, oh yeah, now I remember that. Okay. And the key to this is this plus and minus sign right here. And so we're always going to get two solutions for our quadratic expression. So we fill in all of our values. So right here, the 0.1 right here, this is my ax squared. My negative 1.1782, that's my b for bx. And then my c is this plus 0.07217 value. And so I'm plugging all of these into my quadratic equation, and I get this expression right here, which is a big thing. And now I got to plug it into my calculator. So I'm going to do this twice. Once I'm going to do it where this is a plus, and once I'm going to do it where it's a minus. And I'll get two values out of this. So let's see what those are. All right, so when I solve for this, I get two possible answers. I get x is equal to 10.6, and I get x is equal to 0.064. So at this point, you have to evaluate your answers. Only one of them is going to be reasonable, which means it will give you like a positive value that is less like like if it's a reactant, it's less than what it started with. If it's a product, it's more than what it started with. And of these two, the only reasonable one is 0.064. If I take 0.810 and subtract 10.6, I'm going to have a negative concentration of our reactants, and that just doesn't make sense how we like consume matter that doesn't exist, right? So that means that only the x equals 0.064 is a reasonable value. So we go ahead and we plug that in. Remember our equilibrium concentrations right here. And so this 0.746, this is equal to our 0.810 minus our 0.064. And this right here is just our x value, right? Our product was just going to be equal to x, so it's 0.064. And these are our equilibrium concentrations. And I've solved the problem using a quadratic. It was a little bit more complicated, but the overall process is exactly the same. The only thing that's going to change is how complicated the task of solving for x is. And sometimes it takes a little practice.